Good afternoon, everyone. My name is Juan Santamarta, full professor at the University of La Laguna in the Canary Islands. I would like to share how engineering can help small islands anticipate and adapt to climate change, turning data and design into resilience. The Canary Islands are our testing ground, a living laboratory where we can observe, simulate, and transfer lessons to other archipelagos worldwide. I will guide you through four many parts. First, what climate change means for island water systems, then engineering tools we have developed, SICMA-Canarias and RISK-Agua. After that, I will show you some examples from the Canary Islands. And finally, we will discuss how this experience can inspire broader resilience strategies. First, we are going to talk about water and climate change in islands. On islands, climate change isn't an abstract idea. It's something you can measure in the water balance every year. Hotter air means more evaporation and less effective rainfall. Rain comes in shorter, heavier bursts. A recharge periods shrink, drought lasts longer, and sea level rise brings salinity into coastal aquifers. Fires and heat waves accelerate erosion and water loss. So, as small and steady basins rate fast, the impact cascade quickly through the system. This is where we say in islands, climate change doesn't arrive as a theory, it arrives as drought and stress. Our engineering tool proposed are firstly SICMA-Canarias, climate projection in island. To understand and anticipate these changes, we created SICMA-Canarias, an open climate and a hydrology platform with 100-meter resolution. It integrates past, present, and future data for every point in the archipelago. The platform includes temperature, rainfall, evapotranspiration, aridity, drought indexes, and heat waves. It uses CMIPC climate models under 4 emission scenarios and 3 time horizon: near future, mid-century, and end century. It's co-designed with local sector, water managers, farmers, and tourism planners to make climate science directly useful for decision making. What do you see here are the curve variables we model by working at 100 by 100 meters resolution. We can detect microclimates within each island, something global models simply missed. These projections fit into drought management plans, aquifer protection strategies, and nature-based recharge projects. The goal is to transform uncertainty into actionable design data. Here is what do you see when you get into the platform, the 7 islands and the variables on the left. You can download with this QR code. It's open access, it's free to download. We have an example with the Teidal volcano, the highest point in Spain. Projection saw temperature increasing between 2.5 degrees Celsius and 4.5 degrees Celsius by 2100. Depending on the scenario, rainfall decreases by 15 to 30%. The dry seasons extends by 6 weeks. Wet events become rarer but more intense. The result, faster snow melt, less snow persistence, and declining groundwater research, stressing fragile summit ecosystems. This case shows how localized climate data guides very specific adaptation actions. The whole Canary Islands, using SICMA-Canarias platform, we have obtained detailed climate and hydrological projection for all the Canary Islands at 100-meter resolution. The results are consistent across the archipelago. Air temperature is projected to rise between 1.5 and 2.5 Celsius degrees by the end of the century, depending on the emission scenario, of course. Rainfall is expected to decrease by 15% to 30%, with shorter and more irregular wet seasons. The dry seasons extends by about 6 weeks, and rain events become rarer but more intense, increasing erosion and reducing groundwater research. Evaporation grows, meaning less effective water availability for ecosystems and agriculture. At high elevations such as the Teide area, as we saw before, snow cover declines sharply, leading to lower aquifer recharge. Meanwhile, sea level rise intensifies salinization of coastal aquifers. In short, the SICMA-Canarias results confirm a clear pattern, hotter, dry, and more irregular climates with direct implications for water planning and long-term resilience in the islands. The other tool that we present today is a cascade-failure simulation platform. It's called RISK-Agua. These tools are part of wider European effort, the Horizon Europe Genesis project. It develops nature-based solutions to enhance groundwater recharge and ecosystem service. In the Canary Islands, we are leading a case study in El Hierro Islands involving citizens through the Water Forum and testing MBAs for aquifer recovery. The projects link science, governance, and community participation, showing that technology alone isn't enough, people matter too. The second tool, RISK-Agua, is a digital platform to simulate cascade failures in islands' water systems. It links water, energy, and communication networks through a graph-based model. We can simulate compound events, for instance, a power outage during a drought combined with a pipeline failure. The model calculates a service continuity index, estimating how much of the population still receives water over time. One simulation showed that a single pumping failure could reduce supply to 70% within 4 hours. That's what a cascade really means in practice. This is the platform that we see. We can simulate a landslide in the north of the island of the Hierro in the Canary Islands, and then with that this is the results that we get. On the left, we can see the impact in the critical service. In the middle, the impact in the water infrastructures, and in the right, we can see the crop status. Is the less water that the crops receives. For concluding, we can say that the Canary Islands offer a perfect real-world laboratory for studying how climate and water systems interact in small oceanic territories. Here we can observe climate stress in real time, drought, salinization, recharge decline, and use this data to design test solutions. The partners we detect are not unique. They provide models for other volcanic and archipelagic regions across the world. By combining open data, engineering, and nature-based solutions, the islands are showing how science and policy can finally meet in practice. In short, the Canary Islands don't just adapt, they generate knowledge that can be transferred globally. So what is the takeaway? First, islands are living laboratories where we can observe climate impacts in real time. Second, engineering is more than design. It's the translation of the science into security tools like SICMA-Canarias and RISK-Agua help us anticipate, adapt, and make decisions before crises occur. And third, these approaches are scalable. They can support resilience in many other archipelagos and coastal regions, from data to design, from islands to the world. That is the message that I'd like to remember. Thank you very much for your attention. If you would like to explore these tools or collaborate, please contact me. Our data and platform are open access. So I want to finish with this sentence. Engineering is not just design, it's foresight. Thank you very much.